Acids and bases. Many everyday items like oranges, vinegar, baking soda, toilet bowl cleaners contain acids or bases. Acids and bases are also used in the production of many items such as fertilizers, car batteries, soap, food additives, and plastics. Acids, we find more acids in our food rather than bases because bases taste bitter. But acids are damaging to our teeth because it breaks down the enamel surface. Tooth enamel contains calcium hydroxylapatite, and this reacts with hydrogen ions in acids. So this damage to the enamel makes it soft. So brushing right after eating acidic food or drinking pop is not a good idea. It's better to chew some sugar-free gum because this gets the saliva going, which basically dilutes all of the acid, and then brushing your teeth afterwards. So if your parents say, go brush your teeth, you just ate a whole bunch of candy, you got to tell them, I got to wait 20 minutes for the acids to go away, because otherwise I'm going to brush off the enamel off my teeth. And that causes sensitive teeth and cavities. So there's a couple of theories of acids and bases, and one of the earliest was the Arrhenius theory. And he stated that an acid was a substance that ionizes in water to produce a hydrogen ion. And a base was a substance that dissociated in water to form a hydroxide ion. But this theory didn't always hold up. Some bases don't contain hydroxide ions. They make them when they're dissolved in water. So if you have ammonia and you add it to water, you produce the ammonium ion and the hydroxide ion. So that makes ammonia a base. So if you are a substance that produces H plus ions, you are an acid. If you're a base and you produce hydroxide ions, you're a base. So since then, we've refined the theory, and now we use the Bronsted Lowry concept. And that is that a substance will donate hydrogen ions. So an acid donates hydrogen ions, and a base is a substance that accepts hydrogen ions. So for instance, HCl forms H plus and Cl minus. Because it donates an H plus, it is an acid. Ammonia can accept an H plus to form the ammonium ion, so it is considered to be a base. Acid-base indicators are used to distinguish acids and bases in a lab setting because they will turn different colors at certain pH ranges. We've used phenolphthalein before. In acids and neutral solutions, it's clear and colorless, but in bases, it will turn pink. We've also used litmus paper. So litmus papers, the blue litmus paper will turn red in an acid, and a red litmus paper will turn blue in a base. These are some properties of acids and bases that you might have reviewed last year. Taste. Acids taste sour, bases are bitter. Acids feel like water, but bases are slippery. pH of an acid is less than 7, whereas bases is greater than 7. Indicators, phenolphthalein is the most common, clear and colorless for acids, pink and clear for bases. Litmus paper, blue litmus paper turns red for acids, and red litmus paper turns blue for bases. Safety, both are corrosive and can cause chemical burns, and they are both electrolytes because one will produce hydrogen ions and the other will produce hydroxide ions. Strong versus weak in terms of acids and bases. A strong acid is an acid that ionizes 100% in water. So there's no molecules of acid left in solution, only hydrogen ions and the anion. So hydrochloric acid contains 0 molecules of hydrochloric acid. It's all H plus ions and Cl negative ions. So there's only 6 strong acids. Hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, perchloric acid, and sulfuric acid. All of the other acids are weak. Weak acids ionize less than 50% in water. So this means there's in solution there are some acid molecules, some hydrogen ions, and the anion of the acid, all present in the solution. So strong acid has a single arrow going to the right, but a weak acid will have a double arrow. And this indicates that not all the acid ionizes, and there gets to be something called an equilibrium, a steady state, where the acid molecules and the hydrogen ions and the negative ion all basically stop and their concentrations stay the same. So it happens at it breaks apart into its ions, and the ions reform into an acid at an equal rate. Strong bases are any metal hydroxides from group 1 or 2 with the exception of beryllium. Ammonia is the most commonly used example for weak bases. Strong bases completely dissociate into a cation and the hydroxide ion. There's no formula units of the base in solution, just like there's no molecules of a strong acid in solution. Just like weak acids, weak bases dissociate less than 50%, so there will be base, the cation, and the hydroxide ion in solution at the same time. So again, we would have a double arrow with a weak base and a single arrow with a strong base. Bases only show their basic properties when they're dissolved in water. So use an S if it's solid and AQ when it's dissolved in solution. Okay, strong versus weak, concentrated versus dilute. Strong and weak shouldn't be confused with concentrated and dilute. Concentrated and a dilute is based on how much solute is dissolved in the solvent. Strong versus weak tells us whether or not the molecule ionizes 100% or we still have molecules of the acid in solution. So if I draw a beaker and I say draw a beaker representing a strong acid, perhaps our acid is HA. So this is going to be our strong. So if it's strong in solution, all we have is H pluses and A minuses. If we have a weak acid, HA represents a weak acid, then we will have some molecules of acid present in solution and only some ions. Now, if we have a concentrated solution of acid, let's say a concentrated strong acid, that means we have a lot of acid molecules, or a lot of acid solute rather. So we have a lot of our ions because there's no actual molecules present. So there's lots of acid in our solution, which means there's a lot of ions. If we have a dilute solution of a strong acid, that means we don't have very much acid solute dissolved in water at all. So we would have very few ions of our original acid. So strong versus weak talks about your amount of ionization, how much of it forms ions, and concentrated versus dilute talks about how much solute is actually dissolved in the water. Naming acids and bases. Naming bases is straightforward. It's simply the ionic name for the compound. So NaOH, sodium hydroxide. CaOH2, calcium hydroxide. Acids is a little bit trickier. So first of all, you've got to look and see whether or not there's an oxygen in the formula for your acid. All acids will start with an H, and they will have an AQ. So you're looking here to see if there's an oxygen. If there isn't, then it's just hydro, the element, acid, ic acid. So if it's chlorine, it's hydrochloric acid. If it's HF, hydrofluoric acid. If it is if it has oxygen, that means it's an oxy acid, and it comes from a polyatomic ion. So if it was an 8 ion, like sulfate, it becomes an ic acid. Sulfate would become sulfuric acid. If it is an ite, then it becomes an us acid. Sulfite becomes sulfurous. And then if you've got your per-8, like your halogens, perchlorate, perbromate, and your ites and hypoites, then that also follows into your naming of your acids. So the per-8 ion becomes the per-ic acid. So perchlorate becomes perchloric. Hypoites, hypochlorite becomes hypochlorous. So just these are the most common polyatomic ions, so they are the most common names. So 8 becomes ic acid, and ite becomes us acid. Hydro is only used if there's 2 elements in your formula. Reactions of acids and bases. Acid reactions will fall into 3 categories. You can have a reaction with a metal, and when you have an acid plus a metal, it's a single displacement reaction. You will always form hydrogen gas and an ionic compound. Carbonates. If you have an acid and a carbonate, you will form carbon dioxide, water, and an ionic compound. The ionic compound will come from the negative ion in the acid and the positive ion in the carbonate. Reactions with bases. These are called neutralization reactions. You get an acid and a base, and you will always make a salt, an ionic compound, and water. It says here, what is the net ionic equation for this reaction? So if you split up all of the AQ into their ions, so we've got H plus, Cl minus, Na plus, OH minus, Na plus, Cl minus, and then H2O. So that's your total. So sodium's on both sides. chlorides on both sides. And this happens to be the net ionic equation for any neutralization reaction. You will have, for every H plus, you will have one OH minus, and they will make one water. So if you have two hydrogen ions, two hydroxide, you will make two water. Bases can react with carbon dioxide to form a carbonate, and they often react with oils and fats, but we tend not to examine those as much as we do the reactions with the acids. Okay, the pH scale. The pH scale tells you how acidic or basic your substance is. It ranges from 0 to 14. If you are pH 7, you're neutral. So pH 7 is neutral. And if you are less than 7, you're acidic. And if you're greater than 7, you are basic. It's a logarithmic scale, so every time you go up 1 in pH, that is a 10 times change in concentration. So a base that has a pH of 10 compared to a base that's pH of 9 is 10 times more basic. A base of pH 11 is 100 times more basic than a base of pH 9. So you can see on this pH scale that a lot of our food products are actually acids. Some of them are bases, but only mild, because bases get to be bitter. Okay, to calculate pH. To calculate pH, you need the hydrogen ion concentration. And the formula is pH is equal to the negative log of that concentration. On your calculator, you have a log button. Now, depending on your calculator, depends on whether or not you type in your number. You type in the numbers exactly as they appear in the formula. So for some of you, if I want to find the pH of a solution that has a concentration of 1 times 10 to the negative 3, you type in negative log and then 1.0 exp or EE or times 10 to the negative 3. And that will give you your answer. Some of you, it gives you an error. In that case, you have to do 1 times 10 to the negative 3, then the log button, and then the negative button. It's backwards. So the pH of 1 times 10 to the negative 3 is actually 3.0. When you do significant digits for pH, it has its own rules. So if you look at the number of significant digits in your concentration, so this case there's 2, that is the number of decimal places you have in your pH. So let's do another one. Perhaps we have 6.85 times 10 to the negative 9 moles per liter. And I need to find the pH. So negative log of 6.85 times 10 to the negative 9, or 6.85 times 10 to the negative 9 log negative, depending on your calculator. So this tells us that the pH is 8.16 430 in the calculator, but there's 3 significant digits, so there needs to be only 3 decimal places. So the pH, if the concentration of hydrogen ions is 6.85 times 10 to the negative 9 moles per liter, is 8.164. If you have the pH and you're trying to find the hydrogen ion concentrations, use the inverse or the second function log. It's a 10 to the x button. So basically what you do is you push the second function log and then type in negative and then your pH. So maybe I've got a pH of 4.5. And I want to know what is my hydrogen ion concentration. So some of you will punch this in your calculator exactly like the formula says. Second function 10, and then negative 4.5, and then equals. But on some calculators, you have to do 4.5, and then push the plus negative to make it negative, and then you push the second function log button. So this ends up being, now there's only 1 decimal place, so we only need 1 significant digit in our concentration. 3 times 10 to the negative 5 moles per liter. If you end up with a positive 5, 3 times 10 to the 5, that means you forgot to put in the negative when you did your calculation. Let's do one more. pH of 11. So you're going to put in 10 to the negative 11. So second function log negative 11, or 11 plus minus to make it negative, and then your second function log. So the hydrogen ion concentration for this is 1 times 10 to the negative 11 moles per liter. So that in a nutshell is your introduction to acids and bases, pH, and naming these compounds.